Just to give you an overview of what I'll talk about, so I'll give you a brief introduction to malaria. I won't go into too much of the detail of the biology, but just give you a little bit of the background. And I'll then talk about four different pieces of work that are all related in that they're all about malaria modeling, but they involve different mathematical and statistical methods. So the first one is a multi-scale model of malaria transmission. The second one is multi-species, so looking at not just one species of malaria, but if you have two species of malaria at the same time. And I'll then switch gears a little bit and leave transmission dynamics and move over to spatial mapping. So this is more statistical, looking at spatial mapping of antimalarial drug resistance, but also looking at spatial mapping of disease patterns in order to optimally select future site locations for malaria surveillance. So I promised I'd give a brief introduction to malaria. So malaria is a significant health problem. Every year, the World Health Organization estimates that it results in around 600,000 deaths, and there are over 240 million cases. And if you look at the trends of malaria over the last 23 years, you can see in red here, you have malaria deaths in thousands, and you can see that there's a relatively strong trajectory downwards over the first 12 years of this plot, but then that seems to have stabilized. So there doesn't seem to have been a reduction in malaria-related fatalities over the last 10 years or so. If you look at malaria cases shown in blue, the pattern doesn't seem so obvious. It seems to have it's gone up and it's gone down, but it seems like it's stable around 240 million cases of malaria each year. Over 90% of all of these cases are in Africa, and same with the deaths. So 90% of the 600,000 deaths are occurring in Africa. And the most at risk are those that have significant health complications. And unfortunately, this happens in people groups that we would most likely want to protect. So this is in small infants, in children under the age of 5, and during pregnancy. So malaria biology is really complicated. I don't want to sit here and say that I understand all of malaria biology, but I'll just give you a few bits of information that will be relevant to the modeling and the statistics that I'll present in the talk. So malaria parasites are given to a human when they get bitten by a mosquito that is carrying malaria parasites inside the mosquito. Once those parasites are injected into the human, they may develop symptoms. They may start to feel sick with malaria-related symptoms. There's more than one type of species of malaria. In fact, there are 5 that are known to occur in humans. I'm only going to talk about 3 of the malaria species in this particular talk. So the 3 that I'll talk about are Plasmodium falciparum. So I might refer to that as PF malaria, Plasmodium falciparum for PF. This is the most common in terms of cases because it's very prevalent in Africa, and it's the most common in terms of deaths, again, because of its commonality in Africa. But a large problem with the elimination or the targets that have been set for the elimination of Plasmodium falciparum or PF malaria is that there's drug resistance, and drug resistance has spread throughout the Mekong region, and that resistance to drugs has then made its way to Africa, which has, of course, been catastrophic for the number of deaths due to malaria in Africa. Another type of malaria, another species, is called Plasmodium vivax, and I might call that PV for short. This is the most geographically widespread across the globe. And a complication with PV malaria is that when you get bitten by a mosquito, you'll start to feel sick because of a blood stage infection. But you also have these parasites which make their way to your liver, and they just sleep there for an undetermined amount of time. They will reactivate at some time later and cause another infection. So a single mosquito bite can cause many cases of disease, of your illness. And so this is a complication. That's not the case with falciparum. You get bitten once by a mosquito, you have an infection. If you clear that, you're then not at risk of further disease unless you get bitten again by a mosquito.
So
So Vivax
Jennifer, sorry,
yeah.
in this graph, what is the y-axis? Sorry, I missed it, I
Oh,
think. Yeah.
yeah, no, you're right. It's not
Yeah.
there. That's why.
Uh-huh.
This is the proportion of people that are in different disease states. So if you're blood stage infected or liver stage infected,
Uh-huh.
I'll come back to the model that underpins
I see, I
the
see.
results maybe a little bit later. So this is a complication for Vivax malaria in terms of there's the blood stage infection, which is making you feel sick, but there's also these liver parasites, which will cause later infections. Null's-eye malaria is a strange malaria again, in that it needs a monkey in order to sustain transmission. So you don't get transmission straight from a mosquito to human back to mosquito again. The mosquito has to have bitten a monkey and then bite a human. Or that's the theory, that you need monkeys in order to sustain transmission. But this is very hard to monitor and hard to detect. Often it's misclassified as a different type of malaria. So there's ideas around how we can optimally surveil for the elimination of Null's-eye malaria in different regions. And if that's not enough, you can actually have multiple species of malaria at the same time. So there are parts of the globe where multiple of these malaria species are prevalent. And in particular, in some regions in Asia, there are cases of PV and PF, so Vivax and falciparum at the same time in one person. So yeah, the first modeling that I'll talk about is a multi-scale modeling of malaria transmission, and this is for Vivax malaria only. And the reason it's for Vivax malaria is that it focuses on trying to capture these hypnozoites that can sleep in the liver. So we wanted to build a within-host model of Plasmodium vivax. And as I mentioned before, Vivax control elimination is difficult because of these hypnozoites that can be sleeping in your liver. You might not feel sick, so it might not know that you have these hypnozoites, and then a day later, you can feel sick from malaria symptoms. So we wanted to develop a within-host model of what was happening with these sleeping parasites, and then embed that later in a population level model for transmission. And so we've developed a model that's at the within host level, and it takes into consideration multiple sources of stochasticity. Sorry, was there a question? I'm happy to answer questions throughout. Yeah, so the three levels of stochasticity are that there's random activation of these hypnozoites. So this is a person's liver. And in the liver, there are these parasites which are just sleeping away. Some of them will randomly die at random times, and other of these parasites will activate just individually, and they will cause another blood stage infection, make you feel sick, make you go get treatment, and so on. But each of these can give rise to another set of feeling sick. So that's one level of stochasticity. There's also another level of stochasticity in that each mosquito bite will give rise to a variable number of hypnozoites in the liver, and subsequent mosquito bites will add to that reservoir. So that's the second layer of variability. And then, of course, each person is living in a different environment, and they will get bitten by mosquitoes at different rates based on whether or not they sleep under a bed net or are out at dusk or dawn. So there's also a random stochasticity around the mosquito bite times, given the epidemiological setting that the person lives in. Okay, so we built this up slowly. So first, I'm just going to talk about what happens to a single hypnozoite. So that's just a single parasite living in your liver. What is the fate of that hypnozoite? So hypnozoites, they have to go through a set of compartments where they're sleeping. So when they're in this sleepy or dormant state, they can't activate to cause a relapse or a new infection, but they can die. So the hypnozoites in these K compartments leading up to the point where they can activate, they can always, at a constant rate mu, enter the death compartment for hypnozoites. Once the hypnozoites have progressed through the sleepy or the dormancy state, they can then activate. So once they get to the non-latent compartment, they can activate to then cause another relapse. So this would then make that person feel sick, and the person would go and get treatment, or it would just clear naturally to be a cleared relapse. So the hypnozoites are assumed to die at just a constant rate given the death of the liver cells that they're in. And for a single hypnozoite, this is very similar. In fact, it's equivalent mathematically to a model that was already published several years earlier by Michael White in 2014. The details of the model can be found in two papers by Soumya Mehra, who I should have mentioned before, who was the student working on this a few years ago. So given this compartment structure, we can then write down what this model would look like. So this is the dynamics, remember, just for a single hypnozoite. Here's the same compartment diagram I showed you before. So we can write down a set of Kolmogorov forward differential equations for the probability of a single hypnozoite being in any of the states. And so here are the set of ordinary differential equations that govern how those probabilities change over time. The initial condition is that the hypnozoite enters into the first latent state. So that's the state at which it's sleeping when it first enters the liver. So the initial condition is that with probability 1, it goes into the first latency class. So just to give you an idea, I won't go through all of these ODEs. I'm sure you've probably seen similar things before, but just for an example, if you take the mth compartment in the hypnozoite reservoir, it will increase in probability from the m-1th state, and it will decrease in probability based going to the following state, and it can also die at rate mu, leaving that state. In a similar way, we can construct the other ordinary differential equations, which govern these probabilities. Because of how this has been constructed and because it's quite a sparse system, there's actually an analytic solution to these ordinary differential equations. So the solution to the system can obviously always be written down like this because the system is linear, but normally this exponential, this matrix exponential can't be calculated for arbitrary systems. So this Q here is the transition rate matrix of the set of ODEs. So it's the probability that the probability per unit time of moving from state I to state J of this compartment diagram here. So this is very sparse given all the arrows that you see. So the analytic solution is obviously quite ugly because there's lots of different states, but I'll just give you an idea. So for the mth latent state, the probability at time t of the single hypnozoite being in that state is the probability that at that time it hasn't yet died, so it's survived up until that time. And it's the probability that it's moved through m-1 transitions of the latency to get to that mth state. And a similar thing would apply for the other hypnozoite reservoir states. And you can write down analytic solutions to the other compartments as well, but they're not here just for simplicity. Okay, so we then wanted to extend this model. So this is a model of hypnozoite fate, but it doesn't consider drug. So we wanted to consider what happens when you treat this hypnozoite with antimalarial treatment known as radical cure. So radical cure consists of two different treatments. One is that it takes care of any blood stage infection. So it takes away what's in your blood system that's making you feel sick, the parasites that are multiplying in your blood. But it also targets the liver stage treatment. So it has this dual effect of attacking both the blood stage and the liver stage components of Vivax malaria. So just for simplicity, here I'm taking k equals 0. So I'm just collapsing this hypnozoite reservoir into a single compartment just to show you for simplicity. So here's that simplified model, but the results do apply for k greater than 0. So what we've assumed is that when you get treated with radical cure, any relapse that you're having, so that's your blood stage infection due to hypnozoites being activated, they're cleared instantaneously with a given probability P blood, and that depends on the type of drug that you receive. The hypnozoite in your liver is also killed instantly if you get the liver stage treatment, and that's with some probability P rad. And so if we take these assumptions as given, we can then change the Kolmogorov forward differential equations to include the effect of both liver stage and blood stage treatment. So here you can see the P rad and the P blood coming into the two ODEs for the hypnozoite reservoir and the activated probabilities. And that is at some time S1, which is when the treatment is given, and instantaneously, so it's a delta function. These assumptions could be relaxed if we wanted. But that if we assume that it's instantaneous, the nice thing about that is that we can analytically solve for the probabilities given a single treatment, but also multiple treatments. So this model would extend if you had, say, 5 different rounds of radical cure. That would just be addition of more terms with more delta functions at different times. Okay, so here's just some analytic solutions of what that looks like, just to sort of make it a bit more real. So if you have those 4 states that I showed you before, so you have the hypnozoite state, you have the dead state for the hypnozoite, you have ongoing relapses where it's been activated and then cleared. So what you can see is with probability 1, the hypnozoite starts in the reservoir. And then there's 2 options here. Either you just receive a blood stage treatment, and you can see that blood stage treatment doesn't affect the trajectories for the hypnozoite because it doesn't affect that. It only reduces the probability of being in an active relapse and increases the probability of having a cleared relapse. If you get both blood stage, so that's shown in blue, if you get both the blood stage treatment and the liver stage treatment, what you additionally see is, again, this decrease in being in the active relapse state, but also a decrease in having a hypnozoite in the liver at all. It moves with some probability into the dead state if you get the radical cure, which is both the blood stage and the liver stage treatment. Okay, so that's the model for the dynamics at the single hypnozoite level. I want to now build that up with more complexity into a single mosquito bite. So if we assume a single mosquito bite gives rise to a batch of hypnozoites, so it could be 3, it could be 4, it's geometrically distributed with a parameter. Each of those hypnozoites I'm going to assume undergo the same dynamics. So the dynamics is the model that I just described. So that mosquito bite may give rise to a primary infection, and we assume that occurs with some probability P prim. That may change depending on if you've been bitten recently or what geographical setting you live in. So those hypnozoites that are laid down, that's a geometric random variable for how many there are. Some of them may die, we could see them crossed out, and then some of them will activate and then cause further relapses.
Jennifer, is there any specific reason or a motivation that you choose geometric distribution for this number?
Yeah, there's evidence in the literature that it's geometrically distributed, so we were fine to go with that, but that could be relaxed. There's no reason why it would have to be geometrically distributed, and the results that I show would extend to different distributions as well. But there's evidence in the literature biologically that it's roughly geometrically distributed.
Thanks.
Nice.
Yeah, so if we assume that the hypnozoites are independent and identically distributed, and that is an assumption that we have to make in order to move forward with the model, then tracking the state of all the hypnozoites turns out to be a multinomial distribution. And the probabilities in that multinomial distribution are the analytic probabilities from the continuous time Markov chain, the Kolmogorov forward differential equations that I showed you earlier. Okay, so this is for a single mosquito bite. Obviously, then we want to build up to an epidemiological setting where you have multiple mosquito bites. So we now have an arrival process, which is the biting of the mosquito, which is time dependent, and that's modeled as a non-homogeneous Poisson process. So we have this geometric size arrivals in hypnozoite reservoir. So each mosquito bite gives rise to a random number of new hypnozoites. So you can see here, this person is being bitten 3 times. The first time gives rise to a blood stage infection, P prim, or primary infection. The first bite doesn't, and then the third bite does. And then each bite gives rise to more hypnozoites in the liver, which then have to either die or they have to activate and be cleared. And so you can write down what this looks like in a queue and where the service times in each of the queues, so each of the compartments here is a queue where the hypnozoite is being serviced, and the waiting time is exponentially distributed. So each hypnozoite moves through this network by the within host model, and that has the analytic solutions that I was showing you previously. And we can treat each hypnozoite and infection. If we're okay to assume that they're moving independently through this queue, then the state of the queue is actually analytically tractable in the sense that we can write down a joint probability generating function for the probability of having any number of hypnozoites or infections in any of these queues at a given time. And I'll come back to this. I won't show it to you here, but I'll come back to the probability generating function later. Okay, so again, just to hopefully ground this a little bit, I thought I'd show a simulation. So this is a stochastic simulation using the Doob-Gillespie algorithm for this system, looking at a person that's bitten multiple times. So you can see this person gets bitten. There's hypnozoites that increase in the liver. Some of these clear, some of these give rise to an ongoing relapse. And this person is bitten multiple times. At time 350, we're going to give the drug. And the drug, remember, is a radical cure. So that attacks both the hypnozoites that are in the liver. So you can see the hypnozoites are completely removed. And you can also see that the ongoing relapse that's occurring at time 350 is cleared. This person is then Vivax free in that it has no liver infection and no blood stage infection for a little bit of time, but then gets bitten again. And of course, the hypnozoite reservoir builds up and so on. Okay, so that's the within host model. I wanted to now move on to the population level model. So Population level models for Vivax malaria are quite complicated, and it's for the reason that you can have this unknown number of hypnozoites in the reservoir. So you can have, so normally you think about an SIR model for infection, and that's great, but for Vivax malaria, you can be infected with 0 hypnozoites in the liver, or 1, or 2, or 3, and so on, up to any number. So if you were to truncate at some maximum number of hypnozoites, say like 100 or something, you're ending up with something like 200 ODEs or 202 ODEs in your system in order to track all of the states that you have, which is not really feasible to then extend the model to other things such as age and pregnancy, which are also very interesting for Vivax malaria. So we were hoping to take existing models such as the one in 2014 by Michael White, which had many hundreds of ODEs, and to collapse that down into a very simple population level model, but that embedded the within host model in that and took care of the complexity at the within host level. And this is work that's been done by Anwar, who was a PhD student and has now graduated. So the way that we wanted to do that, so let me just explain. So we have people that are completely susceptible, so they have no blood stage infection and no liver parasites. We have people who have liver parasites but no blood stage infection. And we have people who have blood stage infection. So we have 3 compartments. And so if we're happy to break things down at the population level in that way, we end up with a pretty simple population level model. Sorry. So we have the population model of the mosquitoes, we have a population of the humans, and we have something similar to Ross McDonald type dynamics between the mosquito population and the human population. But the difference here is that we have every time a human is bitten in this model, we have a within host model. So we have these hypnozoites where we can characterize the probability of hypnozoites being in different states for different populations. And the way that we do that is that we track the force of reinfection. So that's the infective bites that are happening over time since the start of your simulation up until the current time. So some of the time-dependent parameters in the population level model involve integrals over time since the start of time of the force of reinfection. So that's the infective bites.
I see.
So what we can do is if we take this compartment model on the left-hand side, we can write down a set of differential equations for each of how each of those is changing. And it's relatively straightforward to do so. And you might think this is a set of ordinary differential equations. But these time-dependent parameters shown in color are actually integrals. So this will turn out to be an integral differential equation system. And so what we have here is, so for example, if you're in the infected class, that means you have a blood stage infection, then with probability P, when you clear that infection, you will move into the susceptible class, but only if you had no hypnozoites in your liver. So if you had any hypnozoites in your liver, with 1 minus that probability, you would move into the H class instead. And similarly, if you're in the hypnozoite class and you only have 1 hypnozoite in your liver, when that hypnozoite dies, you would move into a completely susceptible class. And then activated hypnozoites, we have an average number of activated hypnozoites across the population, and it's with that rate at which people move from a hypnozoite or a liver stage infection to a blood stage infection. And so this is where that probability generating function that I mentioned previously comes in. So using that within host model probability generating function, we can write down the probability for any number of hypnozoites or infections being in any of the compartments at time t. So this is what that probability generating function G looks like. It's an integral over that biting, the force of reinfection, so that involves the biting rate. And it involves lots of other things which come from the analytic solution to the Ford-Kolmogorov equations. And so what we can get from this is the probabilities that we want. So we want P, K1, and KT. So I'm just going to show you the derivation of one of those, which is P, and then I'll leave the others. I won't do them here. So P of T, remember, is the probability that given that you have a current infection, that you have no hypnozoites in your liver. And that we can calculate based on some evaluations of this probability generating function. And you can see it's going to be relatively ugly, but it's just going to be a ratio of integrals of this term here. And so you can write that down in terms of a definite integral. So once we have this model, we can then simulate it. So it's a set of integral differential equations. We can use similar techniques to solving ordinary differential equations, but we have to keep track of these integrals over time.
So how do you track, what kind of, when we try to solve this integral differential equation, we always had some difficulty. Do you use some special package or your
No,
own
so
code?
so we implemented our own solvers, and we used relatively simple like fourth order Ramscutter methods. Yeah.
I see. But you have to cut it out at a certain point for the integral, right? Not you can perform the infinitely large range, right?
That's right.
Yeah,
That's right.
I see.
Yeah.
Okay.
Okay, so now we have this model. Let me show you some simulations. So this first simulation, I'm just showing you that the model that we've constructed, which is in blue, gives back very similar simulations to that huge set of ODEs, which we don't really want to solve, which is shown in red. But at for a given set of parameters, we can obviously solve our model. We can get the probability of being in each of the two different infection classes. So in blood stage infection in solid blue, and in liver stage infection in dashed blue. But of course, using the within host model, we can always at any time, so here at steady state, I'm calculating what is the probability of having any number of hypnozoites. So we can always like reverse engineer what this is from the within host model. Yeah, and then so we also did a sensitivity analysis. Here I'm just showing you one. So if we vary the mosquito to human ratio, we can get very different dynamics. So if you have a very low value of the mosquito to human ratio, then you get no transmission because you're below a threshold where it can't transmit. And then as you increase that parameter, you get very different dynamics. And these are just showing the steady state values for the two different infection classes. The dashed line here corresponds to these parameter sets in the bottom left. Yeah, and so we've thought a little bit about mass drug administration. So if we were to take a population and it has some set dynamics, what if we were to give radical cure to everybody in the population at a set number of times? So here, using the deterministic model, we just gave mass drug administration to the population 3 times. And you can see at each time there's a drastic shift in how much of the population has both blood stage and liver stage infection. But of course, if you're pushing infections down to be very low proportions, the deterministic model starts to be not appropriate, and you should instead move to a stochastic model. So we did a little bit of this, and NY did some of this in his PhD. So here is a very similar model, just implemented at a stochastic level. So instead of using ordinary differential equations, we simulated using a stochastic simulation algorithm. And so here the median trajectories are shown in black, and then the uncertainties are shown in the shaded colors. And you can see one round of mass drug administration on the left-hand side, and then over on the right-hand side, there's 4 rounds of mass drug administration where we've optimized the timing to maximize the chances of disease elimination.
So in the previous slide, the deterministic model seemed like there's no oscillation, but stochastic has oscillation. So what drives the oscillation?
Yeah. Sorry. So in this work, there was no seasonality, whereas in this simulation, this was more realistic. So we actually implemented seasonality based on seasonality of biting rate. Yeah, good question. Okay, so I'll move on from this first piece of work. I'm a little conscious of time. But so I've talked about some hypnozoite dynamics that have been captured with a stochastic model that have analytic solutions that you can embed into the population level model to gain insight into transmission dynamics. And we focused a lot on mass drug administration, both with deterministic and stochastic models, to try and achieve within the model malaria elimination. And we're now thinking about how we can extend this to have multiple spatial populations, as well as, of course, coming back to pregnancy and age structure as well. Okay, so that was the biggest piece of work I'm going to talk about, but I'll now give a little bit of time to species interactions. So this is when people are infected with multiple species of malaria at the same time. And so for this work, which was by Cam Walker, the model was an agent-based framework. So we left behind thinking about compartments in an individual, like in a there are still compartments in terms of infection status, but we're not pulling people together into compartments. And the reason that we wanted to do this is we wanted to consider real treatment strategies that are given to individual patients based on their individual status at different times. And we wanted to compare current practice in Cambodia to different types of practices which have been recommended by the WHO. And that's based on economic modeling about how much it costs and of course the loss to being able to work and what it costs to be sick when you have malaria. Okay, so I'll talk about the agent-based model. So the compartments or the disease status that people can be in for each of the species, so for both falciparum and for Vivax malaria, are shown on the right-hand side. And I'll talk about the dynamics in a cartoonish diagram on the left-hand side, where the colors of the compartments correspond to the colors of the people on the left-hand side. Okay, so the different types of human dynamics that we can have is that we can have infection of susceptible people. So susceptible people can get bitten by a mosquito and become infected. Children are more likely to have a symptomatic infection, so that's in the I class, rather than asymptomatic infection, which is in the A class, which is more likely for adults that have had previous exposure. If you have symptoms, there are 3 options for you. You can receive treatment, or you can pass away from having those symptoms. Or if you don't get treatment at all and you don't die, then you can eventually become asymptomatic. So you still have parasites, but you're not feeling sick anymore. So people from the asymptomatic class, again, there's 3 options for you. You can get picked up by mass drug administration testing and be given a drug, or you can just leave it and eventually recover and go into this green class for recovery. Or for Vivax malaria only, you can recover from the parasites in your blood to have a latent or a liver stage infection, which is L. That's not for falciparum, that's just for Vivax though. So from the treated class, there are a few options. The treatment can fail and you can go back to being asymptomatic. The treatment cannot work at all, it's still failed, but you can die. Or you can recover, the treatment works, or you can just get a blood stage infection treatment and you can go to having hypnozoites in your liver for Vivax only. And of course, you can get reinfected again. So after you've recovered, or if you're still susceptible, you can get bitten by a mosquito again. If you've been bitten recently and you've just come out of being recovered or latently infected, then you're more likely to have an asymptomatic infection than you are to show symptoms. So if you've been allowed to come back to the symptomatic class, you're more likely to go into the symptoms class when you get reinfected. And then only for Vivax, not for falciparum, you can, of course, relapse from those hypnozoites which are sleeping in your liver. And we wanted to consider, so for each of the species, so for Vivax and falciparum, the compartment diagram on the right-hand side is repeated, but we wanted to consider important interactions between the species. And so the interactions that we've considered are these 3 on the left. So we've got masking, which is when you test for malaria symptoms, it's more likely to be detected or to be diagnosed as a falciparum infection than it is a Vivax infection. So falciparum can mask a Vivax infection if you have both. There's treatment entanglement. If you have a mixed infection and you get treated for falciparum, that has a non-zero effect on your Vivax parasites in your system. And also the triggering, which is a really interesting one, where after you've had fever-like illness, such as when you have falciparum malaria, a Vivax relapse, so a hypnozoite waking up, is more likely to happen just after you've recovered from a falciparum infection. So we wanted to consider 3 practices. So we have current practice, which is what's done in Cambodia currently, or like it might be a little bit before now because this was current in 2022. So radical cure is given to only 16% of the population, and this is the population that's allowed to receive it. So not everyone can get radical cure, and the reason for that is one of the drugs that treats your liver stage infection. This can be really bad if you're pregnant, under the age of 6 months, if you're lactating. There's a whole bunch of reasons why you can't receive liver stage drugs, and so it's not given to everyone widely. So current practice is that it's only given to around 16% of people who have either mixed or PV infections detected. An alternative would be to give what's called accelerated radical cure, which is when everyone that comes back as being Vivax infected, either by itself or in a mixed infection, is given radical cure if you can. So that's up to 82% of the population. The rest of the 18% can't receive radical cure because they're pregnant or too young or too old and so on. Another option is to give absolutely everybody that comes back as positive for malaria, including falciparum malaria, radical cure. So this is problematic in that you're giving a drug to people when you don't think they need it, but you're giving it to them anyway. But that's another option for Vivax cure. Okay, so here are some numerical simulations using a stochastic simulation algorithm for this model. So on the left is showing the number of clinical infections over time for falciparum, and on the right for Vivax. And we've got those 3 treatment strategies, either current practice, accelerated, or unified. And I think what you can see is that for falciparum, there's not that much difference between the 3 approaches. But for Vivax, it's quite clear. Current practice is not the best. The other 2 definitely outperform it. And if you look really closely, you can see that the unified radical cure, where you give radical cure to everybody possible, is performing the best, but it's also going to be more expensive because you're going to be giving the drug to people that might not need it, and there might be no benefit to it. So just to wrap up the second piece of work, so I've talked about a multi-species model to capture dependencies between Vivax and falciparum malaria, and used a scenario analysis to show that unified treatment strategy looks like it's the best, leads to the fewest infections and deaths, but of course may lead to extra costs, which is unnecessary. And so in future work, we're hoping to do an economic analysis which actually accounts for this and will make a decision or make some recommendations on what's optimal.
Okay.
Okay, so I wanted to leave transmission modeling behind and now move over to spatial mapping of drug resistance. So drug resistance emerges whenever you expose the parasites to drugs. And this has historically happened to all the drugs that have been used to treat malaria. There's always been resistance that's emerged. And it's this spreading resistance which is a major threat to eliminating malaria. And if we don't isolate increasing drug resistance when we can, it actually puts people's lives at risk if we're using a drug which has already started to fail. So we need to be able to predict drug resistance reliably in space and time. And so with colleagues, I've been working on taking the data that's on the left here and trying to make a model like that's on the right. So you're taking discrete space-time data on the left and trying to make continuous predictions on the right-hand side. So I'll just talk about one particular drug. It's called sulfadoxine pyrimethamine, or just SP. So SP is used for preventative treatments, and it's used for children, infants, and during pregnancy. And the effectiveness of SP has already waned, and we know that resistance to SP is high in certain regions. And it's the prevalence of genetic markers that is used to monitor how effective this drug SP is to protect children, infants, and people who are pregnant. And I won't go into the details, but the genetic mutations, there's lots of them. There are 3 here that are listed, which are thought to be most important. And the way that they've evolved is that it seems like there was a first mutation in this codon 437. Then there was a double mutation. These are mutations at the parasite level at the genome. And then there was a triple mutation involving 3 different markers. And it's an increasing resistance as you gain molecular mutations. And so models that can make predictions at the individual marker are nice and informative. So just an individual marker for 437, for 540, and for 581, that would be helpful. But multi-marker maps would be more ideal. So firstly, I'll just talk about a single marker map which we've developed. So this is a conditional dependency graph on the right-hand side here. So for each of the observations that we have, so that's for each of the dots on the graph of Africa that I was showing before, we have a conditional dependency. So we have the number of samples that are positive for the mutation. That's taken to be a binomial distribution given the sample size and the underlying probability of resistance. So this probability of resistance is modeled using a spatial model. So it's a transformation, so a logit transformation of the sum of 2 components. And the first component is a spatially structured statistical model. So this is a Gaussian process. It has a mean function mu and a covariance function c. I'm not going to go into the details, but I'm happy to answer questions. And it also has a spatially unstructured component, which is additional random noise on top of what the Gaussian process offers. So this model leaves us with lots of parameters to estimate. We have to estimate models which characterize the mean function mu, which is theta m. We have to have parameters which characterize the covariance function, but we also have to have a field value for the Gaussian process at each location where we have data. So this gives us something like 550 or something variables to estimate, or parameters to estimate. And so we do this in a Bayesian setting. Here's the posterior distribution. So the posterior is just written down as a proportionality statement. And it has this binomial likelihood, the Gaussian process prior, and then also priors on all of the parameters in the model. Okay, so I'm obviously skipping over lots of details about what the priors were and other things, but here are some model outputs for three different markers. So on the left, it's going to be 437, in the middle is 540, and the right-hand side is 581. Each of these markers is associated with drug resistance to SP. The top panels show the median of the posterior distributions, and the bottom panels show the uncertainty in the distributions, or the standard deviations. So what you can see is in 1990, some of the areas are covered in very low predicted median resistance. And then you can start to see, as you move from 1990 to 2020, there's this spreading of resistance, particularly in the 540 marker, but also in the other ones as well. And it's the spreading of this resistance that's then led to SP being moved away from as a first-line drug and being swapped out for other drugs. So how can these outputs be used? So here I'm just showing where the 540 marker, so that's this one here, I'm just taking the median. Where does the median reach a different threshold? And I'm using three different thresholds. So I'm using a 5% threshold for where the median reaches 5%, just as an early warning sign, where it reaches 50%, because that's when the WHO suggests this drug can no longer be used for infants, and 90% because that's when the WHO says it can't be used for pregnancy. Remember, SP is also used for children, but there's no threshold that WHO has set where it can't be used. Okay, so here I'm just going to show you an animation of where the model is predicting that the median prevalence of resistance for the 540 mutation has reached these three thresholds. And what you can see is that it starts off in East Africa, and there are locations spreading out from East Africa where the 5% threshold has been reached, and then the 50% threshold, and then obviously eventually the 90% threshold is reached and continues to spread. Right. So this would indicate for us where this drug can no longer be used for infants and during pregnancy. So I mentioned that a multi-marker model would be better, so I'll just briefly talk about that. So a multi-marker model would actually not just look at individual models for each of those three markers, but actually combine them into a bigger model. The problem with that is that none of the data going back to 1990 is consistently collecting that data. Some studies went and looked at just the 437 marker. Some went and looked at the double mutation. Some went and looked at the triple mutation, but there's no consistency over the last 40 years looking at what this data is. So we have to construct a model that allows all of this data to be considered, otherwise we're losing too much data. And so the way that we did that was using a latent variable. So we've denoted here Z, which is the number of each of the marker combinations, which is what we really want to observe. So it's the number of haplotypes of pure wild type up to pure resistant. So what we actually observe, so Z is what we want, but we don't observe it. It's a latent variable. What we actually observe is partially reported data. So we might observe some 437 and then some double mutation and some triple mutation, depending on what the study wanted to collect. So we now need a way to connect these two things. Was there a question? Sorry.
Oh, it's okay. Yeah, go ahead. Sorry.
Oh, okay. Yes, we need a way to connect these two things, and we do that via what we're calling a configuration matrix, which just shows you, which shows you how these two things are connected. So for example, if you went out and collected just the 437 data, well, there are 4 haplotypes which are compatible with that. They all have a 1 in the first position for the 437 marker, and then you have all combinations of 540 and 581 in the other 4 locations. If, for example, you collected the double mutation, so you collected data on 437 and 540, then there are 2 compatible haplotypes. They have to have a 1-1 in the first 2 locations, and then you can have anything you like for the 581 location. And so a configuration matrix for each study has to be constructed. So if you went and did a collection on all of these types of data, you would have to construct your A matrix or your configuration matrix based on what that data is, with ones and zeros based on what's compatible with that data set and what isn't. And so now here's the conditional dependency graph, what this model looks like. It's similar to the one that I showed you before for the single marker, but there are just a few differences. So we still have n observations, so we still have a multiplication in our likelihood from I equals 1 to n. Now we have our partially observed data, which, given the configuration matrix, we can link to those latent variables, which is the number of each of the haplotypes that we don't observe. So if we're happy to marginalize over all of the combinations of those haplotype counts, which are consistent with our partial observations, what we can write down is our likelihood, which is the probability of our partially observed data given those underlying probabilities of each of the haplotype counts. That'd be a set of a vector of length 8 at each location. So this you'll marginalize out all of the Z, which is those latent variables, which are compatible with the observations that you've made. And so this feasible set F has to be constructed for each location where data is collected. That has to be constructed. And so once we're happy with this likelihood, we can then decompose this based on a multinomial likelihood and then an indicator function, because we've chosen the Z to be compatible with the Y. So that's this feasible set F. So given the data that you've observed YI, which is what's being reported, you construct this matrix A, and then you have to find all of the combinations. You have to solve for Z, which are non-negative integers in this linear system. Once we have that, we then again model, we do a transformation to model onto the real line, and then we use a Gaussian process for each of the haplotype, each of the 8 or each of the H haplotype varieties. So this is the outputs of that model. Obviously, again, I'm skipping over lots of details like what the priors are and everything. But here's numerical simulations of what that looks like using Bayesian inference. So this is just for 5 of the haplotypes. I'm not going to show you all 8 because the other 3 are boring in that they're always 0 and they stay near 0. So if you're looking closely, you'll see the most amount of change here in this particular mutation over the 20-year period. And that's because that's the addition of the 540 marker coming in to the haplotype. So this is the addition of that marker, which I was showing the maps of where it's reaching those thresholds over time. So that's the one that's changed the most. But the top row is showing median, and then the bottom row is showing uncertainty. Okay, so I'm getting close to the end. So I've talked about some statistical models of drug resistance and how those model outputs have fed into treatment policy changes. Are then extended from a single marker model to multi-marker models for partially reported data, which is more realistic of what's actually collected. And in future, we're hoping to extend this to a different type of drug called artemisinin, where there's many markers, in fact, many, more than 20. And so these methods are going to have to change because we won't be able to create that feasible set. It will not be possible to enumerate all of the latent variables which are feasible. Okay, so just briefly, I want to talk about some optimal site selection for malaria surveillance. And so this is about, given some data, you construct a geospatial model to create a map, and that might involve some covariates. And then once you have your map, you can hopefully, given some constraints, design an optimal design which you can feed back to people that might be actually collecting data in the field. And so this is something that I've been working on with a PhD student, Lucy Harrison, who just submitted her thesis last week. And so there's a group that have been funded by the Australian government to help try and eliminate monkey malaria or Nolzai malaria in Indonesia. And so remember, this is a complication in that you can't transmit straight from human to human by a mosquito. You have to go from monkey to human via the mosquito. And so what Lucy's been thinking about is if you construct a set of, if you know which districts that you're interested in targeting, then you need to work out, for example, where are the healthcare facilities within that district where people may report their malaria cases to. But for monkey malaria or for Nolzai malaria, it's not that simple because you also have to survey both mosquitoes, but also there has to be monkeys around. So there's 3 different components that you want to think about. Where are the humans going to be reporting, but also where are their monkeys living, and where are their mosquitoes suitable in that habitat. So we've been thinking about how to do this using optimization. So our objective is to find cases of Knowles-Vine malaria. Of course, you could set up a different problem where you want to maximize or minimize something else. But for us, the ideal site to go and surveil is one which has high predicted relative risk of Knowles-Vine malaria and low variance. So here I'm showing, so we're aiming to maximize the ratio of mean to standard deviation of relative risk. And so this is what that map looks like. I'm not going to talk about the model that actually generates that map. It's a bit similar to the modeling that I just showed you previously for drug resistance. So we're thinking about, we want to target sites which are most up in the yellow color, not in the blue color, because they've got the highest predicted mean value of risk and the lowest variance. But of course, we want to collect a number of cases, so we have to think about a catchment. So once we have a site which we're interested in, so that's shown in the red cross, we want to think about how many people filter into that health facility. And so there's multiple ways to think about that. One way is that you just draw a Euclidean circle around that site and people funnel in, or you can think about travel time. So you can think the maximum amount of time people would spend to travel for malaria treatment might be 3 hours, 4 hours, 10 minutes, whatever it is. And then there's information about how long it takes to travel from pixel to pixel. And then this is what that's showing. So these are all the sites which would be able to meet this red cross within 100 minutes of travel time. Once you've decided on what your catchment is, whether or not it's a circle or whether or not it's based on travel time, you of course have to think about whether or not the surrounding catchment area is suitable for both monkeys to survive and mosquitoes to survive, because without those 2, you won't have Knowles-Vine malaria transmission. And so there have been some studies which link Knowles-Vine malaria transmission to these types of covariates. So there needs to be human population, so people need to be living in the area. There should be croplands around, but the forest should be disturbed because that's showing the intersection between monkeys and humans. And there's a relationship with oil palm planting as well. So you can then construct for people who are actually doing surveillance within that catchment, what does this catchment contain? Does it contain all the things you're looking for or just some of them? And so what that means is that we're able to give back to the people that are actually collecting data a list of all the possible health facilities within a district. So here's just a particular district in Indonesia. We've now ranked for these stakeholders the mean objective value. So that was the ratio of mean to standard deviation of the relative risk. So we've now ranked those sites, but we've also given them an idea of whether or not the catchment around that site meets various criteria. And so that can help inform whether or not people or stakeholders would actually then want to go and collect data at these locations. Okay, so in summary of the last piece of work, I've talked about optimal site selection for monkey or Knowles-Vine malaria. And this has been used to direct field studies in Indonesia. And of course, it's not just one site that we want to go and collect data at, it's multiple sites. So there's ongoing work looking at how do you select a set of multiple, how do you select multiple sites optimally? And you might want them to be close together, you might want them to be covering as much area as possible. And then I'm also thinking about how you apply these types of methods to drug resistance. So, and that's in a separate piece of work, which I'm not going to talk about here. How do you pick the best sites to characterize how far and how fast drug resistance is spreading over time? Yeah, so to wrap up in summary, so I've spoken about a few different models, mostly around malaria control and elimination. Obviously, it's very complicated because there's multiple species, there's drug resistance, issues around how to do surveillance optimally. I've presented several models using a variety of different methods, compartment models, agent-based models, and so on. But mostly, I mean, obviously, I'm motivated by mathematical interest as well as trying to use the models to help support malaria control and elimination in different settings. So yeah, I'd just like to thank all these people. The ones that are highlighted in bold are the students or postdocs that were involved in the work. And yeah, thank you very much.
Okay, thanks so much.